Kubernetes Unveiled, Navigating the Core Operating System of the Cloud. Chapter 1, The Digital Landscape and a Looming Problem. Imagine a world where every single digital service you use today, from checking your bank balance to sending a message to a friend, depended on one gigantic, interconnected piece of machinery. This machine was built to perform every function, process every request, and store every piece of data. If one part of this colossal mechanism faltered, the entire operation would grind to a halt. This, in essence, was the dominant model of software in the not-so-distant past, known as the monolith. The era of monoliths, strengths and weaknesses. In the early days of computing, building software meant creating these monolithic applications. Think of it like a single, massive, all-in-one appliance in your home, maybe a gigantic refrigerator that also washes clothes, bakes bread, and cuts your lawn. Sounds convenient, right? One appliance for everything. For a simple household, perhaps. Similarly, early websites and business applications were often designed as single, self-contained units. All functionalities, user authentication, product catalog, payment processing, order history, were tightly woven into one large code base. Strengths, simple to start. For small teams and initial projects, a monolithic structure is straightforward. There's one code base, one deployment process, and everything is in one place. Easy development initially. Developers work within a single project, making it easier to share code and understand the overall flow. Faster communication. All components can communicate directly within the same application, avoiding network delays. Weaknesses, the looming problem. The all-in-one appliance approach quickly revealed its limitations as the digital world exploded. Scaling challenges. What happens when your all-in-one appliance needs to handle double the laundry, triple the baking, and 5 times the lawn mowing? In a monolithic application, if one part, say the payment processing, becomes a bottleneck due to high demand, you have to scale the entire application, even if other parts, like user profiles, aren't under stress. It's like buying 5 new colossal appliances just because your laundry machine is overwhelmed. This is inefficient and expensive. Slow development and deployment. As the codebase grows, it becomes incredibly complex. A small change in one part of the application can have unforeseen ripple effects elsewhere, making testing difficult and slow. Deploying new features means redeploying the entire gigantic application, often requiring downtime, even for minor updates. Technology lock-in. It's hard to introduce new programming languages or technologies because the entire application is built using a specific set of tools. You're stuck with what you started with. Single point of failure. If any part of the monolith crashes, the whole application goes down. Imagine your entire super appliance breaking because the bread maker malfunctioned. Developer bottlenecks. Large teams working on the same monolithic codebase can trip over each other. It becomes harder to collaborate without conflicts. The rise of the internet and the need for scale. Then came the internet explosion. Suddenly, applications weren't just serving a few internal employees. They were serving millions, potentially billions, of users worldwide. The demands on software escalated exponentially, always on. Users expect services to be available 24/7. Downtime, even for planned updates, became unacceptable. Global reach. Applications needed to serve users across different time zones, handling peak loads that varied throughout the day. Instant gratification. Users expected immediate responses. Slow loading times or delayed transactions meant lost customers. Rapid innovation. Businesses needed to introduce new features and adapt to market changes at lightning speed, far faster than monolithic applications could evolve. The old all-in-one model simply couldn't keep pace. It was too rigid, too slow, and too fragile for the dynamic, hyper-connected world emerging around us. We needed a new way to build and manage software, a way that allowed for incredible scale, unwavering reliability, and rapid, independent innovation. This growing predicament set the stage for a fundamental shift in how we approach software architecture, paving the way for the technologies that would eventually lead to Kubernetes. The solution began with a new way to package applications, which we'll explore in our next chapter. Chapter 2, The Journey to Modern Computing, From Servers to Containers. Before we dive fully into Kubernetes, it's crucial to understand the underlying evolution of how applications are deployed and managed. Think of it as a journey from bulky, dedicated machines to lightweight, portable units, each step driven by the increasing demands for efficiency, flexibility, and speed. Physical servers. The early days. In the very beginning, if a company wanted to run a website or an application, they would buy a physical computer server. This server, a powerful machine typically housed in a data center, would be dedicated to running that one application. Imagine a small business deciding to open an office. In the old days, they might dedicate an entire room, perhaps even a whole suite, to a single employee and their desk, even if that employee only needed a small corner. Limitations, underutilization. Servers are powerful. Often, a single application wouldn't fully utilize all the computing power of a dedicated server. This meant wasted resources and money. It was like having a huge, dedicated power plant just to light one light bulb. Slow provisioning. Setting up a new server, installing the operating system, and configuring everything took days or even weeks. This was definitely not ideal for a fast-paced business that needed to respond quickly to new demands. Hardware costs. Each physical server represented a significant capital investment. You had to buy, rack, power, and cool each one. This model was simple, but incredibly inefficient and inflexible as digital demands grew. Virtual machines, VMS, abstraction and efficiency. The first major leap came with virtual machines, VMS. Imagine a large, open-plan office space. Instead of dedicating an entire room to one employee, you could now use partitions to create several smaller, independent offices within that same space. Each partitioned office would still look and feel like a complete, separate unit to the employee working inside it, even though they shared the same building and foundational services. That's essentially what a VM does. On a single physical server, special software called a hypervisor allows you to run multiple independent virtual computers. Each VM has its own operating system, like Windows or Linux, its own virtual hardware, CPU, memory, storage, and functions entirely independently. Benefits: better resource utilization. You could now run multiple applications, each in its own isolated VM, on a single physical server, maximizing the use of its computing power. Instead of having one light bulb per power plant, you could now have many lights drawing power from one plant. Faster provisioning. Spinning up a new VM was much quicker than setting up a new physical server minutes instead of days. Isolation. If one application misbehaved in its VM, it wouldn't affect other applications running in different VMS on the same physical server. One office going offline didn't necessarily mean the whole building shut down. Portability, early form. You could package a VM and move it to another physical server, offering a significant degree of flexibility compared to dedicated hardware. Limitations. While a huge improvement, VMS still carried some baggage. Resource overhead. Each VM still required its own full operating system. Even if your application only needed a small fraction of the OS capabilities, it still had to load and run it, consuming significant memory and disk space. It's like each partitioned office still having its own separate, full-sized reception, kitchen, and bathroom, even if they're rarely or never used. This made them relatively heavy. Slower boot times. Starting a VM still meant booting up an entire operating system, which could take a minute or more. In the fast-moving digital world, even a minute can feel like an eternity. Relative heaviness. While much lighter than a physical server, VMS were still relatively heavy compared to what came next. The container revolution, Docker and its impact. The next paradigm shift was driven by a crucial question. What if we didn't need a whole operating system for every application? What if we could just package the application itself and only the essential components it needs to run, separate from the underlying operating system? Enter containers. Think of a shipping container. It's a standardized, lightweight box designed to hold cargo securely. Crucially, it doesn't matter what kind of cargo is inside, be it electronics, clothes, or perishable goods. The external interface of the container is always the same, allowing it to be easily loaded onto any truck, train, or ship. In the digital world, a container packages an application and all its dependencies, libraries, configuration files, environment variables, into a single, isolated, and portable unit. Unlike VMS, containers share the host operating system's kernel, the core part of the OS. This shared foundation makes them incredibly lightweight and fast to start. Docker, an open-source project launched in 2013, played a pivotal role in popularizing containers. Before Docker, containers existed but were complex to work with. Docker provided user-friendly tools that made it easy for developers to build, ship, and run applications in containers, effectively democratizing their use. Key characteristics and benefits of containers: lightweight and fast. Because they don't carry a full OS, containers are much smaller and start in seconds or even milliseconds. It's like having a dedicated, tiny, specialized tool for each specific task within your workshop, instead of needing a whole new workshop for every tool. Isolated environments. Each container runs in its own isolated environment, preventing conflicts between applications. This is vital for ensuring stability. Consistent across environments, works on my machine. This is perhaps one of the most groundbreaking benefits. Developers often faced the frustrating problem of it works on my machine, but not in testing, or it works in staging, but not in production. This happened because the environments were slightly different. Containers solved this by packaging the entire runtime environment that the application needs. If it works in the container on a developer's laptop, it will literally work exactly the same way in the container on a server in the cloud, because the environment inside the container is identical. This consistency dramatically improved reliability and accelerated the development and deployment process. Portability. Just like physical shipping containers, digital containers can run consistently across different computing environments, from a developer's laptop to an on-premise data center to any major cloud provider. This truly enables build once, run anywhere. The new challenge: managing hundreds, thousands of containers. The container revolution was liberating. Developers could now package their applications into these neat, self-contained units, ensuring consistency and rapid deployment. Businesses saw unprecedented agility and speed in delivering new features. But a new problem quickly emerged. If you're building a complex application with dozens or hundreds of independent services, each neatly packaged in its own container, how do you manage them all? How do you ensure enough copies of your user login service are running to handle sudden spikes in demand? What happens if one of your payment processing containers suddenly crashes? How do you automatically restart it, and on which server, without human intervention? How do all these different containers find and communicate with each other, especially if their locations are constantly changing? How do you update a containerized application with a new version without causing any downtime for your users? How do you automatically scale up or down your entire set of services based on real-time user traffic, day and night? Manual management became impossible at scale. Companies with hundreds or thousands of containers found themselves drowning in operational complexity. This pressing need for intelligent, automated management of containerized applications is precisely what gave birth to Kubernetes. The stage was set for the ultimate orchestrator, which we will uncover in our next chapter. Chapter 3, Enter Kubernetes, the orchestrator's genesis. As we learned in the previous chapter, the rise of containers solved a critical problem: packaging and distributing applications reliably. But with hundreds, even thousands of these identical, portable digital boxes, a new, massive challenge emerged. How do you manage them all efficiently? How do you coordinate their actions, ensuring they work together harmoniously, scale when needed, and recover gracefully when something goes wrong? This is where the concept of orchestration became paramount, and where Kubernetes entered the scene. The Google story, a problem solved at scale. To understand Kubernetes, we must look to its birthplace, Google. For years, Google had been operating at an almost unimaginable scale, running vast numbers of applications and services that served billions of users. Imagine managing Gmail, Google Search, Maps, YouTube, and all their other services simultaneously, each with immense demands for performance, reliability, and constant evolution. Google didn't just use a few servers. They used hundreds of thousands, if not millions, of machines around the globe. To efficiently manage their immense fleet of internal services, they developed a highly sophisticated internal system called Borg. Borg was, in essence, Google's internal operating system for managing vast clusters of computers and automatically deploying, scaling, and healing their applications. It was a pioneering effort in what we now call container orchestration. Later, Google also developed Omega, which built upon Borg's concepts. Recognizing that the container management problem wasn't unique to Google, and in fact was rapidly becoming a universal challenge for every company embracing containers, Google made a groundbreaking decision in 2014. They open-sourced internal learnings and best practices from Borg, releasing it to the world as Kubernetes. The name Kubernetes comes from the Greek word meaning helmsman or pilot, perfectly encapsulating its role as the guiding force behind containerized applications. Google then donated Kubernetes to the newly formed Cloud Native Computing Foundation, CNCF, in 2015, ensuring its independent development and adoption across the industry. What is orchestration? To grasp what Kubernetes does, consider the analogy of a symphony orchestra conductor. An orchestra is made up of many individual musicians, each playing a different instrument. Each musician is highly skilled and knows their part, like an individual container running a single application service. However, without a conductor, the musicians might play beautiful music individually, but they wouldn't play a synchronized, harmonious symphony together. The conductor's role is to coordinate, ensure all instruments start and stop at the right time, direct, guide the flow and emphasize certain sections, manage resources, understand the strengths and limitations of each section and assign parts accordingly, ensure performance, maintain the tempo and dynamics, recover. If a musician misses a cue or needs to rejoin, the conductor helps them synchronize. This is precisely what orchestration means in the context of computer systems and containers. It's the automated process of managing, deploying, scaling, and networking groups of containers. It's about taking many individual services and making them perform as a unified, resilient application. Kubernetes is that conductor. Kubernetes defined, the operating system for the cloud. So, with that in mind, how do we define Kubernetes in a simple yet comprehensive way? Kubernetes is an open-source platform designed to automate the deployment, scaling, and management of containerized applications. But it's more than just a tool. It's often referred to as the operating system for the cloud. Just as your computer's operating system, like Windows, Mac OS, or Linux, manages the underlying hardware, CPU, memory, storage, and enables applications to run on it, Kubernetes manages the underlying computing resources of a data center or cloud environment. It abstracts away the complexity of the physical machines, allowing developers and operators to focus purely on the applications themselves. Its fundamental goal is to simplify and automate the challenges of running applications at scale. Instead of IT teams manually spinning up virtual machines, installing applications, monitoring them, and restarting them when they fail, Kubernetes takes on these laborious, error-prone tasks. You tell Kubernetes, I need 3 copies of my online store application running at all times. Kubernetes then figures out where to run those applications, how to keep them healthy, how to ensure they can talk to each other, and how to handle failures or increase traffic. In essence, Kubernetes transforms a collection of physical or virtual servers into a unified, intelligent platform for deploying and managing modern applications. It's the invisible but mighty force that ensures your favorite digital services are always available, fast, and constantly improving. In the coming chapters, we'll peel back the layers to understand how this cloud conductor achieves such incredible feats. Chapter 4, The Pillars of Kubernetes, Understanding the Core Components. In the previous chapter, we introduced Kubernetes as the conductor or operating system for the cloud. Now, let's peek behind the curtain and understand the fundamental building blocks that make up a Kubernetes system. While its internal workings can be incredibly complex, its core user-facing concepts are surprisingly intuitive once explained through the right analogies. Think of these as the main sections of an orchestra or the key departments in a highly efficient factory. The cluster, the foundation, At the heart of every Kubernetes setup is a cluster. Imagine a cluster as a unified, powerful supercomputer made up of many smaller, interconnected machines. It's not one single box. It's a team of computers working together as a single unit to run your applications. Inside this cluster, there are typically two main types of machine roles. The control plane, also known as the master. This is the brain or the manager of the cluster. It's responsible for making global decisions about the cluster, like scheduling applications, detecting and responding to cluster events, like a failed machine, and managing the overall state. It's typically a set of machines working together to ensure high availability, analogous to the central control room or command center of our factory. Nodes, also known as worker nodes. These are the worker bees of the cluster. They are the machines where your actual applications run. Nodes constantly receive instructions from the control plane and execute the tasks, much like the various production lines or workstations on the factory floor. So, a Kubernetes cluster is essentially a collection of nodes, all managed and coordinated by the control plane, acting as one seamless system for running your containerized applications. Pods, the smallest units. If the node is a production line, what are the individual items being produced or worked on? In Kubernetes, the smallest and most fundamental deployable unit is a pod. Think of a pod like a single, standardized, self-contained shipping crate that holds one or more tightly related items necessary for a specific task. Most often, a pod will contain just one container, which holds your application code, as we discussed. However, sometimes, an application needs a helper process or a sidekick container to work closely with it. In such cases, these perfectly aligned containers can be placed together in a single pod, sharing resources and interacting very closely. Key concept: when your application runs in Kubernetes, it runs inside a container, which in turn runs inside a pod. Why pods? Pods provide a higher level of abstraction than just containers. They are Kubernetes' way of managing individual instances of your application. If a container in a pod crashes, Kubernetes can restart the entire pod. If the node holding a pod fails, Kubernetes can create an identical pod on a healthy node elsewhere in the cluster. Pods are designed to be short-lived and expendable. The beauty of the pod is that it's the standard, interchangeable unit that Kubernetes understands and manages. It hides away some of the container-level complexities from the orchestrator. Deployments, managing your application's lifecycle. If pods are the individual shipping crates, how do you manage hundreds or thousands of them? This is where deployments come in. A deployment is like a blueprint or a master plan for your application. You tell a deployment, I want to run 3 identical copies of my web application, and I want them to be using this specific version of my code. The deployment then takes this instruction and ensures that the desired state is always maintained in the cluster. Declarative power. This is a crucial concept in Kubernetes. You don't tell Kubernetes how to do something, you tell it what you want. You declare the desired state, and Kubernetes intelligently works to make it happen. I want 3 pods running this app. If one pod fails, the deployment notices and tells Kubernetes to create a new one. If you want to update your application to a new version, you update the deployment's blueprint, and it intelligently rolls out the new version, replacing the old ones gradually, without downtime. It even allows you to quickly roll back to a previous version if something goes wrong. Returning to our factory analogy, if a pod is a single manufactured item, a deployment is the automated system in the factory that ensures you always have the right number of items in stock, introduces new models smoothly, and replaces faulty ones without you needing to micromanage each individual unit. Services, the communication network. Now, if you have multiple pods running identical copies of your web application, and new pods are constantly being created or destroyed as needs change, how do users or other applications find them? How do they send traffic to the right pod? Pods are ephemeral, their network addresses can change. This is where services provide stability. A service acts like a fixed, stable address or a permanent phone number for a group of pods. Even if the individual pods behind it come and go, the service's address remains constant. Load balancing. A service also knows which pods are healthy and available. If you have 3 pods for your web application, the service will automatically distribute incoming network requests across all 3 healthy pods, ensuring no single pod is overloaded. It's like a traffic director ensuring traffic flows smoothly to all available lanes. Internal and external. Services can be configured for internal communication, allowing different parts of your own application to talk to each other, or for external access, allowing users from the internet to reach your application. So, if deployments ensure you have the correct number of application instances, services ensure that users and other applications can reliably access them. Namespaces. Organizing your resources. Finally, imagine you're running a very large Kubernetes cluster that handles many different projects, teams, or departments. You wouldn't want Team A's development applications accidentally interfering with Team B's production banking applications. Namespaces provide a way to organize and logically isolate resources within a single Kubernetes cluster. It's like creating separate, virtual workspaces within the same physical cluster. Isolation. Resources in one namespace, e.g., development, are isolated from resources in another namespace, e.g., production. You can define who has access to what, preventing accidental or unauthorized changes. Organization. Namespaces help you manage and identify resources belonging to specific projects, environments, or teams, making a large cluster more manageable. Using our factory analogy, namespaces are like assigning different departments or project teams their own dedicated, clearly marked sections on the factory floor, with their own set of machines, even though they share the same overarching building infrastructure. These 5 concepts, clusters, pods, deployments, services, and namespaces, form the foundational pillars upon which Kubernetes operates. Understanding them provides the crucial context for appreciating the immense power and benefits that Kubernetes brings to modern software development, which is precisely what we will explore in the next chapter. Chapter 5, Why Kubernetes Matters, Key Benefits and Superpowers. We've now explored the journey from monolithic applications to containers and the core components that make up a Kubernetes cluster. But what's the real payoff? Why has this complex system become so indispensable to modern organizations? The answer lies in its ability to bestow a set of superpowers upon applications, transforming how software is built, operated, and sustained. These benefits address the very looming problems we identified in Chapter 1. Automation and self-healing, the resilient guardian. Imagine an application as a fragile plant that needs constant care. In the past, if a part of that application withered, a human operator had to manually intervene, identify the problem, prune the dead parts, and ensure it restarted. This was slow, error-prone, and unsustainable for complex digital gardens. Kubernetes, however, acts as a vigilant, ever-present gardener, endowed with advanced automation and self-healing capabilities. It constantly monitors the health of your applications. You tell Kubernetes your desired state. For instance, I want 3 copies of my online store's payment processing service to always be running and healthy. Automation. Kubernetes continuously compares the current state of the cluster with your desired state. If a pod, a containerized instance of your application crashes, Kubernetes detects it instantly and automatically starts a new one to replace it. It's like having an autopilot that not only flies the plane, but also performs emergency repairs mid-flight if a system fails, without needing human intervention. Self-healing. If an entire machine, a node, goes offline, Kubernetes recognizes that the pods running on it are no longer available. It then intelligently reschedules those pods onto other healthy nodes in the cluster. This automatic recovery significantly reduces downtime, increases application reliability, and frees up human operators from tedious, reactive firefighting. This dramatically improves resilience, ensuring applications remain available even when underlying infrastructure experiences issues. Scalability, elasticity on demand. One of the most powerful and visible benefits of Kubernetes is its ability to scale applications up and down almost effortlessly. In the monolithic era, scaling meant buying more hardware or building entirely new copies of a colossal application, which was slow and expensive. With Kubernetes, thanks to its container-based architecture, scaling becomes incredibly agile. Horizontal scaling. If your application experiences a sudden surge in traffic, say, millions of people flocking to an e-commerce site during a flash sale or a new product launch, Kubernetes can automatically create more copies, more pods of the application to handle the increased load. When the demand subsides, it can scale them back down, conserving resources. It's like a magical banquet hall that expands or shrinks its dining area based on the number of guests arriving, adding or removing tables and chairs as needed, instantly. Vertical scaling, less common for applications themselves, but often for nodes. While scaling pods generally means horizontal growth, more instances, Kubernetes also allows for managing the growth of the underlying infrastructure by intelligently adding or removing nodes to the cluster as overall resource demand fluctuates. This elasticity ensures that your applications can gracefully handle fluctuating user demand without manual intervention, preventing slowdowns or crashes during peak times. Load balancing. The traffic controller. When you have multiple copies of your application running, you need a way to distribute incoming user requests evenly across them. This is the role of load balancing, a feature seamlessly integrated into Kubernetes through its services concept. Even distribution. As new requests for your application come in, the Kubernetes service acts as a smart traffic controller. It automatically directs each request to a healthy and available pod, ensuring no single application instance becomes overwhelmed. It's like a sophisticated roundabout where traffic is constantly guided efficiently to the least congested exit. High availability. If one of your application pods becomes unhealthy, the load balancer instantly detects it and stops sending traffic to that troubled instance. Requests are only sent to the healthy pods, ensuring users always get a responsive experience. This quiet but powerful capability ensures smooth performance and uptime, even when parts of the system are under extreme pressure or experiencing issues. Portability, build once, run anywhere. A significant challenge in the past was that applications were often tied to specific environments or cloud providers. Moving an application from an on-premise data center to the cloud, or from one cloud provider to another, could be a massive undertaking, often requiring significant re-engineering. This led to vendor lock-in. Kubernetes fundamentally changes this. Because applications are packaged into standardized containers and Kubernetes provides a consistent orchestration layer, your applications become inherently portable, consistent across environments. An application running in a Kubernetes cluster behaves the same way whether that cluster is in your own data center, on Google Cloud, Amazon Web Services, Microsoft Azure, or even at the edge, closer to where data is generated, like a smart factory. Avoiding vendor lock-in. This freedom means businesses have more flexibility. They can choose the best underlying infrastructure for their needs without being permanently tied to one provider or even run applications across multiple environments simultaneously, hybrid or multi-cloud strategies. This write once, run anywhere philosophy empowers organizations with unprecedented flexibility and reduces reliance on a single technology provider. Resource efficiency. Maximizing hardware value. In the days of physical servers, and even with early VMS, server hardware often sat idle or underutilized because organizations provisioned enough capacity for peak demand, which occurred only a fraction of the time. This was a classic case of wasted investment. Kubernetes, with its intelligent scheduler, aims to maximize the utilization of your underlying server infrastructure. Intelligent scheduling. When you tell Kubernetes to run an application, it doesn't just randomly plop it onto a server. The Kubernetes scheduler intelligently analyzes the resource requirements of your application, how much CPU, memory it needs, and the available resources on each node. It then places the application on the most suitable node, optimizing overall resource distribution across the cluster. Bin packing, think of it like a smart game of Tetris. Kubernetes tries to fit as many application pieces as possible onto the existing server blocks, ensuring minimal gaps and maximum use. This leads to higher density, meaning more applications can run on fewer physical machines. This optimized resource utilization translates directly into cost savings, as you get more mileage out of your hardware or cloud spend. developer productivity and agility, empowering innovation. Ultimately, all these technical benefits converge to enable a crucial human benefit, empowering developers and accelerating innovation. Focus on code, not infrastructure. With Kubernetes handling the complexities of deployment, scaling, healing, and networking, developers can concentrate on what they do best: writing great application code, building new features, and solving business problems. They no longer need to worry about the intricacies of the underlying servers. Faster development cycles. The consistency provided by containers and Kubernetes means that an application built on a developer's laptop will behave exactly the same in testing and production. This eliminates countless hours of debugging environment issues. Combined with automated deployments, it means new features and bug fixes can go from a developer's keyboard to users in minutes, not days or weeks. Enabling DevOps. Kubernetes is a cornerstone of the modern DevOps movement, which promotes collaboration and automation between development and operations teams. It provides a shared, consistent platform that both developers getting their code shipped and operations, keeping services running, can understand and utilize efficiently. In essence, Kubernetes is not just making computers work better. It's making people work better, enabling organizations to be more agile, responsive, and innovative in a rapidly changing digital world. In our next chapter, we'll look at some real-world examples of how companies are leveraging these superpowers to achieve remarkable results. Chapter 6, A Day in the Life with Kubernetes, Use Cases and Real-World Impact. In the previous chapter, we explored the superpowers Kubernetes bestows upon applications: automation, scalability, portability, and more. Now, let's bring these abstract benefits to life by looking at how real companies, from tech giants to traditional enterprises, are using Kubernetes to deliver their services, solve complex problems, and innovate at an unprecedented pace. You might not see Kubernetes directly when you interact with an app, but its invisible hand is almost certainly guiding its performance. The DevOps connection, accelerating innovation. Before we dive into specific examples, it's worth understanding the concept of DevOps. This isn't a specific technology, but a cultural and technical movement that seeks to bridge the gap between development, the people who write the code, and operations, the people who run and maintain the code. The goal of DevOps is to increase an organization's ability to deliver applications and services at high velocity. Kubernetes is a foundational technology for DevOps because it enables continuous integration and continuous delivery, CI/CD. Imagine a frictionless assembly line for building and deploying software. Continuous integration, CI. Every time a developer writes new code, it's automatically tested to ensure it hasn't broken existing functionality. Continuous delivery, CD. Once the code passes tests, it's automatically prepared and packaged for release. With Kubernetes, this means building a new container image and updating the deployment. This allows companies to deploy new features or bug fixes multiple times a day, instead of once a month or even less frequently. This automation frees up developers to focus on writing innovative code, while operations teams gain a consistent, stable platform for management, reducing manual errors and accelerating the entire software lifecycle. Microservices architecture, the Lego approach to software. Many of the companies adopting Kubernetes are also embracing microservices architecture. Recall from Chapter 1 that traditional, monolithic applications were like a single, giant, all-inclusive machine. Microservices takes the opposite approach. It breaks down a large application into a collection of small, independent, specialized services. Think of it like building with Lego bricks. Instead of one giant, indivisible structure, you build your application from many small, specialized bricks, microservices, each responsible for a single function. One brick for user authentication, another for product catalog, a third for payment processing, and so on. Each microservice can be developed, deployed, and scaled independently. If your payment processing service needs an update, you don't have to redeploy the entire application. You only update that one service. If your user authentication service is experiencing high load, you can scale only that service, not the entire application. This approach offers incredible agility and resilience, but it also introduces complexity, managing hundreds or thousands of these small, independent services. This is precisely where Kubernetes shines. It acts as the perfect operating system for microservices, providing the orchestration needed to automatically manage, connect, scale, and heal all those individual Lego bricks, ensuring they work together seamlessly to form the complete application. How companies leverage Kubernetes, real-world examples. Let's look at some specific instances. Spotify, orchestrating the world's music. Spotify, the globally leading audio streaming service, faced an immense challenge of scale. With hundreds of millions of users streaming music globally, their infrastructure needed to be incredibly robust, constantly available, and highly scalable. They were an early adopter of containers and microservices, and in 2018, they famously announced their full migration to Kubernetes for their core infrastructure. Spotify used Kubernetes to manage the thousands of microservices that power their entire music streaming platform. This allowed them to handle massive scale, easily scale up or down the number of servers and application instances based on demand, whether it's lunchtime in Europe, evening drive time in the US, or a new album release from a top artist. Accelerate feature development. Engineers could develop and deploy new features and updates for their specific microservices quickly and independently, without affecting other parts of the platform. This means that features like personalized recommendations, new social sharing options, or improved search functionalities can be rolled out much faster. Improve resilience. If a particular service experienced an issue, Kubernetes could automatically detect it and restart it, or shift its workload to healthy instances, ensuring continuous playback for users around the world. For Spotify, Kubernetes isn't just a piece of tech, it's a critical enabler of their rapid innovation and consistent global music experience. Airbnb, navigating growth and evolution. Airbnb, the popular online marketplace for lodging, experienced explosive growth, which put immense pressure on their original monolithic application. As they grew, updating and scaling this single, large code base became a bottleneck, slowing down innovation. Airbnb embarked on a journey to break down their monolith into microservices, and Kubernetes became the ideal platform to manage this new, distributed architecture. By leveraging Kubernetes, Airbnb could support rapid iteration. Engineers could work on specific parts of the platform, like booking, search, or messaging, in isolation, deploying updates and new features independently and without constant coordination with other teams. This helped them keep pace with the demands of a fast-evolving market. Improve site reliability. Kubernetes' self-healing capabilities allowed Airbnb to run their vast number of services with greater confidence. Issues in one service were less likely to cascade and take down the entire platform, improving the overall reliability of their marketplace. Optimize resource usage. With automated scaling and resource management, Airbnb could ensure they were efficiently using their cloud infrastructure, paying only for the resources they needed at any given time. Kubernetes provided the stable, scalable foundation necessary for Airbnb to continue its rapid global expansion and deliver a seamless experience for hosts and guests. Goldman Sachs, modernizing a financial giant. It's not just tech giants that benefit. Even highly regulated, traditional institutions like Goldman Sachs are embracing Kubernetes. As a global financial services firm, they manage an enormous amount of data and execute countless transactions, demanding extreme levels of performance, security, and compliance. Modernizing their applications was crucial to stay competitive. Goldman Sachs uses Kubernetes to build a private cloud platform within their own data centers, allowing them to increase efficiency and agility. By containerizing traditional applications and running them on Kubernetes, they can deploy and manage their financial tools, risk analytics, and trading platforms more efficiently. This means faster updates to critical systems, maintains stringent security and compliance. Kubernetes provides mechanisms to enforce strict security policies and isolation, which is paramount in the highly regulated financial industry. They can ensure that sensitive data remains protected and that their systems meet all regulatory requirements. Attract and retain talent. Working with modern, cutting-edge technologies like Kubernetes makes the firm more attractive to top engineering talent. These examples demonstrate that Kubernetes is incredibly versatile. Whether you're streaming entertainment, booking travel, or executing complex financial transactions, Kubernetes is providing the underlying muscle and intelligence, quietly ensuring these services run smoothly and efficiently. Beyond web applications, while many examples focus on web-based services, Kubernetes utility extends much further. Data processing. It's used to manage large-scale data pipelines and analytics workloads. Machine learning, AI, ML. Kubernetes provides an excellent platform for deploying, training, and managing machine learning models, allowing organizations to operationalize their AI initiatives. Batch jobs. Even one-off, scheduled tasks can be managed and run reliably on Kubernetes. In summary, Kubernetes is not just a trend. It's a fundamental shift in how organizations manage their digital operations. By providing a robust, automated platform for deploying and scaling applications, it empowers businesses to be more agile, resilient, and innovative. In our next chapter, we'll delve into the vast ecosystem of tools and services that have grown around Kubernetes, making it even more powerful and adaptable. Chapter 7, the Kubernetes Ecosystem, a universe of tools and services. By now, you understand that Kubernetes is a powerful orchestrator, the operating system for the cloud. But just like a computer's operating system isn't useful in isolation, it needs applications, drivers, and utilities. Kubernetes thrives within a rich and diverse ecosystem of tools and services. This ecosystem extends Kubernetes capabilities, simplifies its operation, and integrates it seamlessly into broader cloud and software development workflows. Think of it this way. Kubernetes provides the core infrastructure, the stage, and the lighting for your show. The ecosystem provides all the specialized props, backstage crew, sound systems, and even the ticketing platform to make the entire production run smoothly, optimally, and securely. Managed Kubernetes services, simplifying the core. When Kubernetes was first gaining traction, setting up and managing a cluster yourself was a significant endeavor. It required deep expertise in distributed systems, networking, and security. For many organizations, the operational overhead was daunting. This challenge led to the rise of managed Kubernetes services offered by major cloud providers. These services essentially take over the heavy lifting of running the Kubernetes control plane, the brain of the cluster, as discussed in Chapter 4. Google Kubernetes Engine, GKE. Given that Kubernetes originated at Google, GKE is often considered the most mature and feature-rich managed service. Google itself runs much of its own infrastructure on a highly similar system. Amazon Elastic Kubernetes Service, EKS. Amazon Web Services, AWS, the largest cloud provider, offers EKS, which integrates deeply with other AWS services. Azure Kubernetes Service, AKS. Microsoft Azure provides AKS, offering a robust managed experience within the Azure cloud. Benefits of managed services: reduced operational burden. The cloud provider takes care of upgrades, patching, security, and ensuring the control plane is highly available and resilient. You just focus on running your applications. Seamless integration. They integrate naturally with other cloud services like databases, networking, and identity management. Scalability. They can easily scale the underlying infrastructure as your needs grow, often with automatic provisioning of new nodes. For many companies, especially those without large, dedicated infrastructure teams, managed Kubernetes services are the gateway to leveraging Kubernetes without the significant upfront operational investment. Monitoring and logging. The eyes and ears of your applications. Running applications at scale requires constant vigilance. You need to know what's happening inside your cluster and with your applications at all times. This is where monitoring and logging tools come in. Monitoring, what's happening now? Monitoring tools collect and analyze metrics, numerical data about the performance and health of your applications and the Kubernetes cluster itself, e.g., CPU usage, memory consumption, network traffic, error rates. They provide dashboards and alerts. Common tools in the Kubernetes world include Prometheus for collecting time series data and Grafana for creating visually rich dashboards. Analogy. Imagine the instrument panel in an airplane cockpit. It tells you altitude, speed, fuel levels, engine temperature, critical real-time data needed for safe operation. Logging, what happened? Logging tools collect and store all the text-based output generated by your applications and the Kubernetes components. This is crucial for debugging problems and understanding past events. A popular combination for logging is the ELK stack, Elasticsearch, Logstash, Kibana, which allows for centralized collection, processing, and visualization of logs. Analogy. This is like the flight recorder or black box of an airplane. It records all communications and system data, allowing investigators to reconstruct events after an incident. Having robust monitoring and logging in place is essential for maintaining application reliability and quickly responding to issues in a dynamic Kubernetes environment. CI/CD pipelines. The automated software factory. We touched upon continuous integration and continuous delivery, CI/CD, in Chapter 6. These automated pipelines are central to modern software development, and they integrate seamlessly with Kubernetes. Once a developer commits new code, a CI/CD pipeline automates the entire process: building, compiling the code, and generating the application. Testing, running automated tests to catch bugs. Packaging, creating a new container image that contains the application and its dependencies. Deployment, pushing that new container image to a repository and then instructing Kubernetes to update the running application using that new image. Popular CI/CD tools that integrate well with Kubernetes include Jenkins, GitLab CI/CD, and GitHub Actions. These tools act as the automated levers and pulleys that streamline the journey of code from a developer's workstation into production, leveraging Kubernetes for the actual software delivery. Service meshes, advanced network control. As microservices architectures grow increasingly complex, simply allowing services to communicate might not be enough. You might need advanced control over how they interact, with features like intelligent traffic routing, advanced security policies, and deep observability of inter-service communication. This is where service meshes come into play. A service mesh is a dedicated infrastructure layer that handles service-to-service communication. Rather than managing these concerns within each application, the service mesh layers on top of Kubernetes, transparently handling things like traffic management, routing requests dynamically, A/B testing new versions, security, encrypting communication between services, enforcing access policies, observability, collecting detailed metrics and traces of every network interaction. Prominent service meshes include Istio, developed by Google, IBM, and Lyft, and Linkerd. While adding another layer of complexity, service meshes are invaluable for very large, highly distributed applications that require fine-grained control over their network interactions. Serverless and Kubernetes. The best of both worlds. You might have heard of serverless computing, where developers write code and don't worry about servers at all. The cloud provider automatically spins up resources to run the code in response to events and then shuts them down. While sometimes seen as an alternative to Kubernetes, they can also work together. Native, an open-source project built on Kubernetes, allows you to run serverless workloads on top of your Kubernetes cluster. This means you get the benefits of serverless, automatic scaling to zero, event-driven execution, but within an environment you control, providing greater flexibility and avoiding vendor lock-in specific to certain cloud providers' serverless offerings. It essentially turns your Kubernetes cluster into your own private serverless platform. Other essential tools, expanding capabilities. The ecosystem continues to grow, with numerous other tools adding valuable functionalities. Helm, often called the package manager for Kubernetes. Helm simplifies the deployment and management of complex applications. Much like app stores simplify installing software on your phone. It allows you to define, install, and upgrade even the most complex Kubernetes applications with a single command. Operators. These are specialized pieces of software that extend Kubernetes capabilities, allowing it to manage complex applications with specific needs, like databases or AI platforms, as native Kubernetes objects. An operator knows how to deploy, scale, backup, and upgrade that specific application type automatically, akin to a robot expert for a particular type of task. This vast and dynamic ecosystem is a testament to Kubernetes' flexibility and its centrality in the cloud-native landscape. It means that while Kubernetes provides the strong foundation, the tools built around it offer specialized solutions for virtually any operational challenge a modern application might face. It's this collaborative and evolving universe of software that truly amplifies what Kubernetes can do, helping organizations navigate the complexities of cloud computing, though it also introduces new considerations, as we'll discuss in the next chapter. Chapter 8, Navigating the Challenges, What to Consider. We've spent considerable time exploring the immense power and benefits of Kubernetes, from its self-healing capabilities to its role in enabling rapid innovation. It's clear why so many organizations, from startups to enterprises, are adopting it. However, like any powerful technology, Kubernetes is not a silver bullet, and its adoption comes with its own set of challenges and considerations. Understanding these potential pitfalls is crucial for anyone looking to leverage Kubernetes effectively. Complexity and the steep learning curve. Perhaps the most frequently cited challenge with Kubernetes is its inherent complexity and the steep learning curve it presents. While we've simplified its core concepts through analogies, the reality is that the number of concepts, components, and configurations involved in a full-fledged Kubernetes deployment can be overwhelming. Analogy. If driving a car is like managing a single application manually, flying a commercial jet plane is like operating a Kubernetes cluster. While both get you from point A to point B, the jet requires extensive training, understanding of complex systems, and continuous monitoring of numerous gauges and controls. Skill investment. To truly harness Kubernetes, organizations need to invest heavily in training their teams. Developers need to understand how to design applications for a containerized, distributed environment. Operations teams need to grasp the intricacies of managing, troubleshooting, and securing clusters. This requires a significant time and resource commitment. Talent scarcity. Given its relative novelty and complexity, finding experienced Kubernetes professionals can be challenging, leading to competitive hiring and higher salaries. This initial hurdle in understanding and mastering Kubernetes often dictates whether an organization chooses to manage it in-house or opts for a managed service. Security, a multi-layered challenge. Security is paramount for any digital system, and Kubernetes, by its very nature as a distributed system, introduces new layers of security considerations. While Kubernetes provides robust security features, they must be correctly configured and continuously monitored. The responsibility for security is shared. Container image security. The foundation of your application is the container image itself. This image must be free of vulnerabilities, and its contents should be regularly scanned and updated. Cluster security. This involves securing the Kubernetes control plane components, ensuring only authorized users and services can access and modify the cluster. It also means securing the communication within the cluster. Network security. Defining how applications within the cluster can communicate with each other and how they can be accessed from outside requires careful network policy configuration. Access control. Implementing strict access controls, who can do what in the cluster, is critical to prevent unauthorized changes or data breaches. Neglecting any of these layers can create significant vulnerabilities. Organizations must adopt a comprehensive security strategy that covers the entire software supply chain, from the moment code is written to its deployment and execution within Kubernetes. Cost management, efficiency versus expenditures. One of the benefits of Kubernetes is resource efficiency, allowing you to run more applications on less hardware. However, this doesn't automatically translate into lower costs, especially when running Kubernetes in the public cloud. Complexity of billing. Cloud billing for Kubernetes environments can be intricate, often involving charges for compute, virtual machines, networking, storage, and the managed service fees themselves. It can be challenging to pinpoint exactly where costs are accumulating. Underutilization risks. While Kubernetes aims for high resource utilization, poorly optimized applications or over-provisioned clusters can still lead to wasted cloud spend. If you automate scaling improperly, your cluster might grow far larger than necessary and stay that way, racking up bills. Operational overheads. The investment in skilled personnel, tools for monitoring and management, and continuous optimization efforts all contribute to the total cost of ownership. Effective cost management requires continuous monitoring, right-sizing of resources, and potentially leveraging reserved instances or spot instances. Cheaper, but less reliable cloud resources, where appropriate. When Kubernetes isn't the answer, avoiding overkill. Despite its widespread adoption, Kubernetes is not always the right solution for every problem or every organization. There are scenarios where implementing Kubernetes can be overkill, introducing unnecessary complexity and cost. Small, simple applications. If you have a single web application with modest traffic that rarely changes, running it on a few simple virtual machines or even a basic web hosting service might be perfectly adequate and significantly simpler to manage. Using Kubernetes for such a scenario is like buying a super heavy-duty industrial blender just to make a daily smoothie. Small teams with limited resources. If your team is small and lacks dedicated expertise in cloud-native technologies or DevOps, the learning curve and operational overhead of Kubernetes can be a drain on productivity rather than an enabler. Legacy applications. While it's possible to containerize older, monolithic applications, they often don't benefit from Kubernetes' distributed nature without significant re-architecture into microservices. Trying to force a square peg into a round hole can lead to more problems than solutions. Infrequent updates. If your application changes very rarely, the benefits of automated deployments and rapid iteration offered by Kubernetes might not outweigh the management complexity. Before jumping on the Kubernetes bandwagon, it's crucial to assess your specific needs, team capabilities, and the nature of your applications. Sometimes, simpler solutions are indeed better. In-house management versus managed service. A strategic choice. The decision of whether to run Kubernetes yourself, on your own servers or unmanaged cloud instances, versus using a managed service, like GKE, EKS, AKS, is a critical strategic choice, often influenced by the challenges mentioned above. In-house management. Pros: maximum control, deepest customization, potential for cost savings at very large scales if efficiently managed, ideal for specific compliance or security requirements. Cons: high operational burden, requires significant in-house expertise, responsible for patching, upgrades, and high availability of the control plane, can be a major distraction from core business activities. Managed services. Pros: significantly reduced operational overhead. Cloud provider handles the control plane, easier to get started, quicker problem resolution in many cases, often integrates seamlessly with other cloud services. Cons: less control, you're limited by the provider's choices. Potential for vendor lock-in. Though Kubernetes itself is open source, the specific integration with cloud services can create dependencies, can be more expensive at very high scales if not optimized. Most organizations, especially those in early stages of Kubernetes adoption or with smaller infrastructure teams, find the benefits of managed services far outweigh the costs and limitations. It allows them to focus on their applications rather than the underlying orchestration platform. Understanding these challenges is not meant to deter you from Kubernetes, but to provide a balanced perspective. With proper planning, investment in skills, and strategic choices, these hurdles can be overcome, allowing organizations to fully leverage the transformative power of this technology. In our final chapters, we will explore where Kubernetes is heading and how to continue your learning journey. Chapter 9, The Future of Cloud Computing, Where Kubernetes is Heading. Having journeyed through the origins, mechanics, and real-world impact of Kubernetes, it's natural to wonder, where is this technology headed? Is it a fleeting trend or a foundational shift that will continue to shape the digital landscape for decades to come? All indications point to the latter. Kubernetes is not just here to stay. It is rapidly evolving, expanding its reach, and becoming an even more integral part of the cloud computing paradigm. Edge computing, extending Kubernetes to the frontier. One of the most exciting frontiers for Kubernetes is edge computing. Cloud computing typically means centralizing data processing and storage in large data centers far from the source of data. Edge computing, however, brings computation and data storage physically closer to the sources of data generation. Think smart factories, retail stores, IoT devices, or even autonomous vehicles. Why is this important? For applications that require ultra-low latency, near-instantaneous response times, or where connectivity is unreliable, processing data locally at the edge is crucial. Imagine a robot in a factory needing to react in milliseconds, or a smart city sensor processing traffic data without sending it all back to a distant cloud server. Kubernetes is uniquely positioned to manage applications at the edge. Just as it orchestrates containers in large data centers, it can manage applications deployed on a vast network of smaller, geographically dispersed edge devices. Projects like K3s, a lightweight Kubernetes distribution designed for resource-constrained environments, are making it easier to deploy and manage Kubernetes on smaller devices, making it the control plane for the hyper-distributed future. This expansion means that Kubernetes won't just be the operating system of the cloud, but potentially the operating system for the entire distributed network, from massive data centers to tiny IoT devices. AI/ML workloads, the brains behind the automation. Artificial intelligence and machine learning, AI/ML, are transforming industries, and they need powerful, flexible platforms to train and deploy their sophisticated models. These AI/ML workloads are often complex, requiring specific hardware, like specialized graphics processing units, or GPUs, and significant computational resources, often in bursts. Kubernetes is increasingly becoming the platform of choice for managing these demands. Resource management. Kubernetes can schedule AI/ML jobs on specific nodes equipped with GPUs, ensuring these valuable resources are efficiently utilized. Scalability for training. Training complex AI models often involves parallel processing across many machines. Kubernetes can spin up and tear down the necessary computational resources on demand. Model deployment. Once an AI model is trained, it needs to be deployed as a service that can respond to requests in real time. Kubernetes is perfectly suited for managing the deployment, scaling, and high availability of these inference services. Projects like Kubeflow specifically aim to make machine learning workflows, from data preparation to model deployment, easy to run on Kubernetes. This signifies Kubernetes' evolution beyond just traditional web applications to become a core engine for the next generation of intelligent systems. Further abstraction and simplification. Kubernetes for everyone else. While Kubernetes excels at managing containers, its steep learning curve remains a barrier for many. The future will likely see continued efforts to abstract away its underlying complexities, making it more accessible to a broader range of users, especially developers who just want their code to run without needing to become Kubernetes experts. Platform engineering. More and more companies are building internal developer platforms on top of Kubernetes. These platforms provide developers with a simplified interface to deploy and manage their applications, without directly interacting with Kubernetes, YAML configurations, or command line tools. Such platforms allow developers to focus on application logic, while platform engineers handle the underlying Kubernetes complexity. Managed services evolution. Cloud providers will continue to enhance their managed Kubernetes offerings, adding more automation, easier integration with other services, and more robust operational capabilities, further lowering the barrier to entry. Higher-level abstractions. New tools and frameworks will emerge that sit on top of Kubernetes, offering even simpler deployment models. This could manifest as more advanced serverless capabilities built into Kubernetes or declarative APIs that allow users to define applications at a much higher business logic level, leaving Kubernetes to figure out the infrastructure details. The goal here isn't to replace Kubernetes, but to make it disappear from the developer's everyday view, much like you don't need to understand how your computer's operating system manages processes to simply open a web browser. The enduring legacy, a foundational technology. Kubernetes has already achieved a status rarely seen in the fast-paced world of technology. It has become a de facto standard. Its open-source nature, robust community, and widespread adoption by all major cloud providers and thousands of enterprises have cemented its position as a foundational technology for the foreseeable future. Cloud-native foundation. Kubernetes is the bedrock of the cloud-native movement, enabling organizations to build and run highly scalable, resilient applications that take full advantage of cloud computing models. Digital transformation enabler. For many companies, Kubernetes is a key component in their digital transformation journeys, allowing them to modernize aging IT infrastructure and become more agile and competitive. Continuous innovation. The vibrant open-source community around Kubernetes ensures continuous innovation, with new features, tools, and integrations being developed at a rapid pace. Just as Linux became the dominant operating system for servers and Android for mobile devices, Kubernetes has emerged as the dominant orchestration platform for containers and cloud-native applications. Its core principles of declarative management, automation, and distributed systems have fundamentally reshaped how software is delivered and operated at scale. As we look to the future, it's clear that Kubernetes will continue to be a central player in the evolution of computing, underpinning everything from personalized recommendations and instantaneous financial transactions to autonomous vehicles and cutting-edge artificial intelligence. It truly is the core operating system of the cloud, guiding us into an increasingly complex, yet seamlessly orchestrated digital future. In our final chapter, we will summarize the key takeaways from our journey and provide you with a compass for continuing your exploration of this fascinating and powerful technology. Chapter 10, Your Kubernetes Compass, Next Steps and Resources. We've reached the end of our journey through the world of Kubernetes. From understanding the problems that necessitated its creation to exploring its core components, undeniable benefits, real-world impact, and future trajectory, you now possess a foundational understanding of this transformative technology. Our goal was not to make you a Kubernetes expert overnight, but to demystify it and provide you with a mental model to understand its significance in the modern digital landscape. Before we chart your course for further learning, let's briefly recap the key takeaways. Key takeaways recap. The evolution from monoliths to containers. We began by understanding the limitations of monolithic software, which struggled with scaling and agility, leading to the adoption of virtual machines, and then, crucially, containers. Containers revolutionized how applications are packaged, making them lightweight, consistent, and portable. The orchestration challenge. While containers solved packaging, they introduced a new problem: managing thousands of them at scale. This set the stage for orchestration. Kubernetes as the cloud operating system. Born from Google's internal systems, Kubernetes emerged as the leading open-source platform for automating the deployment, scaling, and management of containerized applications. It acts as the intelligent helmsman of your digital fleet. Foundational pillars. We learned about its core concepts: a cluster composed of a control plane and nodes, pods as the smallest deployable units, deployments for declarative application management, services for stable networking and load balancing, and namespaces for organization and isolation. Unlocking superpowers. Kubernetes grants applications capabilities that were once difficult or impossible to achieve. Automation and self-healing. Chinese letter, Chinese letter, Chinese letter, Japanese 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 letter, Japanese letter, Chinese letter, Chinese letter. Scalability. DEM-a-ND, Japanese letter, Chinese letter, Japanese letter, Japanese letter, Chinese letter, Chinese letter, Japanese 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 symbol, Japanese letter, Japanese letter, Japanese letter. Load balancing. Chinese letter, Chinese letter, Japanese 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 letter, Chinese letter, Chinese letter. Portability. Japanese letter, Japanese letter, Japanese letter, Japanese letter, Chinese letter, Chinese letter, Japanese letter, Japanese letter, Chinese letter, Chinese letter, Japanese letter, Japanese letter, Japanese letter, Chinese letter, Chinese letter, Chinese letter. Resource efficiency. Japanese letter, 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 Chinese letter, Chinese letter, Chinese letter, Japanese letter, Chinese letter, Chinese letter, Chinese letter, Japanese letter, Japanese letter, Chinese letter, Chinese letter. Increased developer agility. Chinese letter, Chinese letter, Chinese letter, Japanese 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 letter, Chinese letter, Chinese letter, Japanese letter, Japanese letter, Japanese letter, Chinese letter, Chinese letter. Real-world impact. We saw how companies like Spotify, Airbnb, and Goldman Sachs leverage Kubernetes to deliver services at immense scale, innovate rapidly, and modernize their operations. It's the invisible backbone of many services you use daily. A thriving ecosystem. Kubernetes is supported by a vast ecosystem of tools and services, including managed cloud offerings, robust monitoring solutions, CI/CD pipelines, and specialized extensions, all working to enhance its capabilities. Navigating challenges. We acknowledged that Kubernetes comes with a learning curve and requires careful consideration of security, cost management, and whether it's truly the right fit for every scenario. The future is bright. Kubernetes is expanding into new frontiers like edge computing and AI/ML, poised to remain a foundational technology as cloud computing continues to evolve and abstract away complexity for developers. You've embarked on an important intellectual journey. Understanding Kubernetes is no longer just for engineers. It's becoming increasingly vital for business leaders, strategists, and anyone looking to grasp the future of digital infrastructure. How to learn more, your Kubernetes compass. If this book has sparked your curiosity and you wish to delve deeper, here are some practical pathways and resources for continued learning. The official Kubernetes documentation, kubernetes.io, this is the definitive source of truth. While it can be dense, it's incredibly comprehensive. Start with the concepts and tasks sections to solidify your understanding of the components and how they interact. Don't be afraid to read and reread sections. It's a detailed technical manual. Online courses and certifications. Many platforms offer structured learning paths. Coursera, Udemy, edX, Pluralsight, a cloud guru. Search for courses on Kubernetes fundamentals or cloud native. Look for those taught by experienced instructors with practical examples. Linux Foundation and Cloud Native Computing Foundation, CNCF, certifications. If you're looking for a formal validation of your skills, consider the Certified Kubernetes Administrator, CKA, for operations roles, or the Certified Kubernetes Application Developer, CKAD, for developers. These are challenging but highly respected certifications. Community and events. Local meetups. Search for Cloud Native or Kubernetes meetups in your city. Meeting experienced practitioners and asking questions in person can be invaluable. CNCF and Kubernetes Slack channels. These online communities are vibrant places to ask questions, learn from others, and stay updated on the latest developments. KubeCon plus Cloud Native Con. This is the flagship conference for the Kubernetes and Cloud Native community. While attending in person might be a big step, many of the talks are recorded and available for free online, offering insights into the cutting edge of the technology. Hands-on experience, even without a big budget. Minikube/Kind. These free tools allow you to run a full-fledged Kubernetes cluster directly on your laptop. While not for production, they are excellent for experimenting and gaining practical experience. Cloud provider free tiers. Major cloud providers Oz, Google Cloud, Azure often offer free tiers for their managed Kubernetes services, EKS, GKE, AKS, which can allow you to experiment with small clusters without incurring significant costs. Always monitor your usage to avoid unexpected bills. Recommended reading. The Phoenix Project by Gene Kim, Kevin Bayer, and George Spafford. While not about Kubernetes directly, this classic novel elegantly illustrates the principles of DevOps and why modern practices, which Kubernetes enables, are so crucial for business success. Designing Data-Intensive Applications by Martin Kleppmann, a more technical but incredibly insightful book that deep dives into the principles of distributed systems, many of which Kubernetes embodies. Conclusion: your digital future. Kubernetes is more than just a piece of software. It's a paradigm shift in how we approach building and running the digital services that power our world. It represents a powerful abstraction layer, allowing us to think about applications and their needs rather than the raw infrastructure underneath. By providing you with this Kubernetes compass, we hope you feel more confident navigating the discussions around cloud computing, digital transformation, and the infrastructure that underpins our interconnected lives. The digital world will only continue to grow in complexity and scale, and Kubernetes, the operating system for the cloud, is poised to guide much of that future. Thank you for joining us on this journey. We hope you feel empowered to continue exploring the fascinating world of cloud-native computing.